Okay, I think we're good to go. Welcome everyone to this presentation in Percona Live 2021. Today we're going to discuss about geospatial implementation when it comes to MongoDB search. We are three people that are presenting today. Myself, Antonio Giannopoulos. I'm a database administrator in Rackspace, focusing in MongoDB. And I have with me like two ex-colleagues of mine and very good friends, Pedro Albuquerque, who is working as a database engineer in WISE for almost 4 years now, and he has 10 years experience with databases, MariaDB, MySQL, and Mongo mainly. Outside of work, he plays handball and also has an interest in reported film photography. I have also Alex Cercel with me from Palantir Technologies. He works as a database engineer, and his team is managing the company's NoSQL databases. Today, we're going to present three different data stores when it comes to geo implementation: Mongo, ES, and Postgres, which we think are the most common one that they used for geo implementations. We're going to use a very common application type which serves restaurants. For this application, we will describe common functionalities like proximity searches with filters and ordering. We will present obviously best practices and append a couple of benchmarks to help you understand the strengths and the weaknesses of each data store. Let's, before we start, let's have a quick look to our data set. Our data set consists of New York restaurants. We downloaded our data set from that URL that you see there. It's from Mongo Inc. But we populate ourselves the price range, the cuisines, the rating, and the amenities array. We randomly generated the fields, so feel free to laugh if you see a Golden Arches restaurant serves sushi. Our app is very simple. The customer wants to find suitable restaurants near him, and that's the functionality that we're going to describe. We start with MongoDB. MongoDB for geospatial representation supports two formats, GeoJSON and the legacy coordinate format. Technically, there isn't much difference, but I prefer GeoJSON more because it's more rich and it's a more modern format than the legacy one. GeoJSON supports multiple types of geometry, but on our examples and in real-world application, most probably you're going to use two of those, the point and the polygon. On the slide, you also see an example of a MongoDB document of our dataset. MongoDB standard optimization when it comes to speed up geo operation is adding a geospatial index. There are two types of indexes, the 2D and 2D sphere. We are going to deal with 2D sphere, and more specifically with the version 3 of that index that was introduced in Mongo 3.2 that has some really nice optimization. Geo indexes must index geometric data. For the field that you actually try to index as 2D sphere. If you don't, it will print an error. At the same time, those indexes are sparse by default. So it won't care much about null documents, if you have any, for that particular field. But for non-geometry data, like an integer or a string, it will give you an error. They can be compound, but they cannot be part of your shard key. So if you think with those indexes that you can do something like a geographical distributed sharded cluster, there is a different way to implement it. It's not geo indexes. The most common query on a restaurant application is get me the points near me. Restaurants near me in a radius of 100 meters. There are two commands for this functionality in MongoDB. GeoWithin is the first command, and you can see the syntax on the slide. It uses rads, not meters or miles. In order to convert the rads to kilometer, we divide with 6,378.1. There's another number for miles. It doesn't need a geospatial index, but an index will speed it up for sure. Results don't come in a proximity order. You will get the results back into the physical order, the order that they're stored in the index or in the collection. Also supports a limit, which actually boosts the performance. When you use a limit, you're going to scan fewer keys on your index. The next operator that supports the proximity query is near-sphere. The difference here lies that the fact that it needs a 2D sphere index, it uses meters, obviously, instead of rads, in the max and min distance, which are like an upper and down bounds when you search an area. And the results, that's the most important difference. The results come ordered by distance, with the closest first. The limit works here, it will limit the results, but doesn't work the same way as on GeoWithin. So if you use a limit, it will give you less results back, but you're going to scan the same amount of documents. Because it has to fetch them first, order them, and then give it back to the driver. Same thing applies if you use min and max instead of a limit to paginate. If your application only supports near-me operations, it would be useless. We need to be able to combine the near-me with other predicates and form complex queries, like give me Japanese restaurants near me or restaurants with rating 4 and above. Both GeoWithin and near-sphere support filters, and most importantly, Mongo support compound geospatial indexes. And you can see that the compound index boosts the performance no matter what the key order is, but the key order here matters. If you choose to reverse the key order, you might get better performance, like geo first and the predicate after, or the predicate after and the geo next. Another important operation is to order the restaurants by criteria, different than the distance, like price, for example. Both GeoWithin and near-sphere support $sort on different fields. The main difference is that with GeoWithin, you're going to get the results sorted based on the sort predicate that you're going to define. While with near-sphere, you're going to sort twice. It's going to order internally by distance and then order by the predicate that you provide. So GeoWithin is more suitable when the distance is not an issue. For example, 100 meters. You don't actually care if you're going to walk like 99 meters or 10 meters. It's pretty much the same. But be aware that the sorts here would happen in memory. Unless you do a trick. If you reverse the order in the index, put the sort first, and you add like a find operator that you pretty much search for everything on that field, then you can use the index to actually get your results back ordered. But the trade-off is that you're going to scan more index keys. On Geosphere, that trick doesn't work because it performs two sorts, if you remember, both distance and the order by field. So no matter the order you're going to use, you're still going to get them back. You're still going to get an in-memory sort. And here on this slide, we demonstrate the difference on the order that you get the results. We run the exact same query for GeoWithin and GeoNear, and as you can see, we get different order of the restaurants. Same restaurants, but in different order. MongoDB offers a GeoNear operator as well on the aggregation framework, which is very similar to Geosphere, but it has a cool feature that it can return straight away the distance between the points. You can do that on your driver as well. You just need to run some calculation, but that command will give it to you back. That operation requires a GeoWithin index and must be first on the aggregation pipeline. These are the limitations. Finally, you may also need to determine in which area a customer is in order to suggest restaurants nearby based on area metadata. For example, if I am in Times Square, give me the restaurants in Times Square using the Times Square tag rather than running a GeoQuery. GeoIntersect is the operator that provides you that functionality. And you can see an example on that slide. Now, our application relies on static points, which makes things easier. But if, for example, we had moving points like cabs or taxis, it's a little bit of a game changer. Moving points means we need to constantly track their location, which add writes into the mix. If you're updating the location on an object too frequently, you may host the database with writes, but if you don't do it very frequently, you won't be accurate. You need to find, obviously, the perfect mix and pass some of that responsibility to your driver. You also need to scale the writes. pass the responsibility to the driver. If a taxi, for example, is stuck in traffic, don't update the database. Remember your last location and don't update it if it hasn't changed. Some best practices on this slide, I'm going to go through those really quick because it's what we described. Geospatial indexes will always boost the performance. Always use a limit because it's going to be beneficial, especially with GeoWithin. Control the document size because if you're using sort, you're going to do in-memory sorts. Use GeoWithin for proximity that you don't care about the order. Use metadata that will narrow your searches. Use more secondaries that you might tag them with locations that, they're hotspotted, like Times Square, for example, in our data set. And know your queries, because random geo-queries can actually hurt your performance. And here, I have some benchmarks that they prove pretty much what we mentioned. We compare GeoWithin with GeoNear on the first graph, and you see the difference in performance. GeoWithin runs way faster because it doesn't have to do that in-memory order by the distance. But as we increase the radius, that difference fades because the search now is more expensive than the sort. The number 2 is the hack that we did with the sort, and you see that it always, like on our dataset, operates way faster than without the hack with an in-memory sort. Number 3 is very impressive, limit versus no limit on GeoWithin. With limit, you always get the same performance. Without the limit, your performance goes up like in a linear fashion, I would say. And number 4 is we run the exact same query from Times Square and Statue of Liberty. It's the exact same query, but you see the difference in execution time because it takes way more time to find restaurants from the Statue of Liberty. There's nothing, it's surrounded by sea. So that's an example of like, be careful of your queries. And I'm passing to Pedro for Postgres.
Hi, everyone. Let's now talk about geo implementation in Postgres and how an extension can help here. So the extension I'm talking about is PostGIS, and it allows geographic information systems objects to be stored in the database. This extension includes support for the GIS-based R3 spatial indexes and functions for analysis and processing of GIS objects. PostGIS also adds extra types, geometry, geography, for example, functions, operators, and index enhancements that apply to these special types. It also provides support for importing, exporting shapefiles, and many other features. PostGIS gives you a choice of 2 different ways to store geospatial data. One is geometry. It is an older type that has many more functions supporting it. It assumes all of your data lives on a Cartesian plane, so it's like a map projection. It has greater support from third-party tools, and operations on it are usually faster. Geometry is also best if you are pretty comfortable with spatial reference systems, or you are dealing with localized data where all your data fits in a single spatial reference system, or you need to do a lot of spatial processing. The other data type is geography. It is a newer data type that supports long-range distance measurements, but most computations on it are slower than they are on geometry. It assumes that your data is made up of points on Earth's surface, specified by latitudes and longitudes. Geography type will give you more accurate results than geometry, especially over long distances. And with this data type, you don't need to learn much about planar coordinate systems. Geography is generally best if all you care about is measuring distances and lengths, and you have data from all over the world. PostGIS supports multiple types of geometric objects, but for our examples, and for most of the applications out there, the most common types are point and polygon. Indexes make using a spatial database for large data sets possible. Without indexing, a search for features would require a sequential scan of every record in the database. So the B3 index is not very useful for spatial data, since it only supports storing and querying data in a single dimension. Data such as geometry, which has 2 or more dimensions, requires an index method that supports range query across all the data dimensions. One of the main advantages of Postgres for spatial data, it offers several kinds of indexes which work well for multidimensional data. One example are the GIST indexes. These indexes break up data into things which overlap and things which are inside, and can be used on a wide range of data types, including GIS data. PostGIS uses an R3 index implementation on top of the GIST to index spatial data. For tables that are mostly read-only and where a single index is used for the majority of queries, Postgres offers the cluster command. This command physically reorders all the data rows in the same order as the index criteria, yielding 2 performance advantages. First, for index range scans, the number of 6 on the data table is drastically reduced. And second, if your working set concentrates to some small intervals on the indices, you have a more efficient caching because the data rows are spread along fewer data pages. The most common query on the restaurant app is get me the points near me. For example, restaurants near me in a radius of 100 meters. There is one command for this functionality. It's the std within. For geography data type, it uses meters. But on the other hand, for geometry, it can use degrees, and this depends on the used spatial reference system of geometries. For queries where Postgres filter has to remove more rows, Postgres does a bitmap heap scan on the GIST index. You notice the optimizer uses the intersects operator with the stexpand function. To do a bounding box search using the index and no filtering, make use of the intersects operator. For geometries, the intersects operator means bounding boxes overlap or touch. In the same way that for numbers, the equals operator means values are the same. The reason the intersects operator is useful is because if a special index is available to speed up the test, the intersects operator will make use of this. This can make our queries much, much faster. One note here is before version 1.3, stexpand was used with stdistance to do indexable distance queries. But this complex construct has been replaced by the simple std within function. When it comes to ordered results, they don't come ordered by distance. So a trick needs to be done. You can see in the slide an example on how to order results by distance. We can combine the near me with other predicates and form complex queries like using the example Antonius mentioned earlier, to give me the Japanese restaurant near me. You can do this having 2 approaches. One approach is using a couple of indexes, one GIST index on geography data type, and one B3 index on using column. When both columns are needed, Postgres can combine the 2 independent indexes using a bitmap index scan. The other approach is to create a compound GIST index on both columns. However, you cannot create this compound index without the B3 GIST extension. This extension is a module providing sample GIST index operator classes, which implement B3 equivalent behavior for many data types. This is one simple example of how composite indexes come at help in near-me operations with multiple filters. Using the previous example, Postgres needs to apply a filter to the gist index results when there is only a gist index on geography data type. That filter does not happen when using the compound index on geography and text, which makes it way more efficient. Here are a couple of conclusions on the radius query. We compared geography and geometry data types and queries using a similar radius. It proves that geography is slower than geometry data type. On the right-hand side, the more matched points, the longer time it takes to execute the query. Obviously, there are more restaurants in Manhattan than near the Statue of Liberty.
Cool. And now we're down to Elasticsearch. For the field types for the geo implementation in Elasticsearch, we have the GeoPoint, which takes the simple longitude and latitude pairs, and it also supports GeoJSON and also the legacy notation. And you also have the more advanced field where you can basically store lines, circles, and other types of geometric shapes. One thing to mention here is that if you rely on dynamic mappings, Elasticsearch is not going to do a good job. So once you're storing the data, you might end up with a different field type. So every time you want to use geo points or geo shapes, try to design the mapping first, which for Elasticsearch, it's recommended in all the use cases, but usually it does a better job. In this case, it didn't do a good job at all. So I had to create the mapping before. Next slide, Antonius. So Elasticsearch-Geo runs on BKD trees, which is an implementation of the KD tree, which basically splits a plane in two subplanes. And this makes the location of the entry as well as the indexing itself considerably faster. There's some animations here, Antonio, so just do some forward clicking, please. So every time you write a point, it's going to split the plane in two other subplanes. And once you are doing the search for that, it's going to look at the, let's say we have these points stored. We're looking for an H which has the coordinates 7 and 8. And it's going to look at, first of all, split the X plane. So it's going to look on the X coordinate. It's going to go to C, which has only one relation, the point D. And then on point D, also it splits the X plane, so it's going to look to the left or to the right. Since I said 7 and 8, it's going to look to the right of it, and then we're going to end up with the H with the coordinates 7 and 8 in the plane from between C, D, and F. Next slide, please. In terms of the geo-queries, we have the geo-bounding box, which basically takes in an upper left and lower right point, and then it creates the bounding box. We have the geo-distance, the geo-polygon, which is deprecated in the recent versions, and we have the geo-shape query, which takes different parameters like intersection, outside the intersection, contains, within, and so on. Next, please. Here we took the geo-distance query. The distance defaults to meters. So I said 100 there, so it was looking for 100 meters, and then it takes a location. The location is the interesting point for us, and all the geo searches come under the filters. And on the right-hand side, we have a response saying that we found 31 hits. We hit one shard, and the query was fairly fast initially, and then all the filters from Elasticsearch are getting stored in the caches. So if you are running the same search again, it's going to come back considerably faster. Next. In terms of if you are trying to look for additional filters, you can run a terms and look for a specific term and also apply the same geodistance. In this case, I used cuisines for the Japanese, and I found from the 31 restaurants, 5 are Japanese. The ordered proximity. So you can sort, in this case, I sorted by price, the same query, and you can use the geodistance to add an additional level of sorting, which is going to sort obviously by distance. Next, the area search, I used the geopolygon, and we got the Midtown South coordinates. So within those coordinates, I found 10 restaurants, and I used a collapse, which basically creates unique records. So all those were within the Midtown South area. In this case, this is an aggregation because apart from the queries, we also have some aggregations. I'll talk about them a bit more in the next slide, but this one was a geodistance aggregation, and basically looking at the coordinates for a specific field, we basically sorted based on 3 different distances. So we looked at what restaurants are within 100 meters, between 100 meters and 200 meters, 200 to 300 meters. Again, here I used the unit M, but as in previous examples, you could set any units, but it defaults to meters. In this case, I just added it. I could have left it out. In terms of the aggregations, we have quite a few interesting options. So we have the geodistance, geohash, geotile grid aggregations in terms of the buckets. So it's creating different sections with records from those aggregations. And then we have the metrics aggregations, the geobounds, which basically creates the upper left and lower right within that are containing the interesting points that we're looking for. The geocentric that finds the center of the coordinates that we gave it, and the geoline, which basically can draw a path on a map.
Okay, and some closing remarks and thoughts. The data structures used by Postgres and Elasticsearch are more suitable for heavy geo workloads than MongoDB. That's very obvious. It's a B3 versus like Spatial type of indexes. All 3 databases support a rich command set, so you can do pretty much whatever you want with those. But PostGIS looks to have the richest command set. We actually saw some operations there that actually blew our mind. Elasticsearch works out of the box. You don't have to do anything. Mongo needs indexes, obviously, to optimize the geo operations. And Postgres requires the extension to be installed. You need to be like a little bit more advanced user in Postgres to do extensions. All 3 provide various scaling mechanisms for geospatial workloads. And if we had to choose one, it would be, I don't know, if we were in a class now, I would ask you to raise your hands. We cannot do that online. But I think we would use like PostGIS just because it looks more enterprise. And thank you. And if you have any questions, I know that's only 1 minute left, but we're happy to answer them. Else, you can hit us with a direct message. Okay, I don't see any questions. I want to thank Percona one more time for allowing us to present in this virtual conference, and I hope next year we can be in an actual room and we present face to face, and you can raise your hands. What's your favorite data store?
Thank you, everyone.
Yeah, Mark,
Thank you, everyone.
I think the recordings will be available at some point from Percona. So yes. Right. Thank you.
Thank you. Bye.